Hello, welcome to Math County, and today we are going to talk about limits, derivatives, and integration. Okay, so just a quick overview of these three important and related topics in calculus. Now, first, let's talk briefly about limits. So for limits, for example, say you have a function f of x equals 16 minus x squared all over x minus 4. So here, if obviously you can see that when x is equal to 4, the function is indeterminate. So if x equal to 4, we have 16 minus 16 over 4 minus 4, which is in 10 equal to 0 over 0. And obviously, this is indeterminate, right? So what limit does is, limit helps us to determine what actually happens as the values of x approaches 4, right? So we can have limit as x approaches 4, limit as x approaches 4 of 60 minus x squared all over 4, x minus 4. So we can actually simplify this and then get, this is 4 squared minus x squared, right? So then this is x minus 4 maintained. So obviously the numerator becomes, we just apply difference of two squares here, and then we have 4 minus x, 4 plus x, all over x minus 4. Okay, so I think there was a little bit of a misformulation here. So I'm going to take this, I'm going to wipe this. So that's x squared minus 16. So x squared minus 16, which is x squared minus 4 squared, which is x squared, x minus x minus 4, x plus 4. So now we have limit as x approaches 4, x plus 4. So we then insert the 4 into the expression, and then we have what? X plus 4 equals 4 plus 4, and then we have 8. So as the values of x approaches 4, the limit of f of x is actually 8. So limit basically helps us to determine what happens when the values of x approaches 8. So how about derivatives? What are derivatives? So when we talk about derivatives, derivatives simply help us to find the slope of the curve of a function, right? So say you have, you plot a curve, like so, right? And then you want to find the slope of the curve. Say the function here is equal to f of x, right? So all you have to do is to find the derivative of f of x, and that's to say we have the x will then be equal to f prime of x. So f prime of x basically represents the slope of the function. So now we talk a bit about integration. So basically all that integration is telling us that is integration is actually used to find the area under a curve, right? So say we have this same curve, okay? So we have points A to B, and we need to find the area under this curve. Integration actually helps us to find the area under this curve, right? Okay, and one more thing, integration is actually the opposite of differentiation. So if we have the derivative here as f prime, if we integrate the derivative of f prime, then we have integral f prime of x dx, and this brings us back to f of x plus some constant c. Okay, so that is the general overview of limit, derivatives, and integration. So let's talk about limits. Okay, let's talk about limits as we will return to differentiation and integration later on. Okay, so for limits, let's consider this function. Say we have a function y. We have a function y equals, say, x squared, right? So if we graph this function, this is a rough sketch, okay? So keep in mind that this is just a rough sketch. Okay, so we have yx, okay, of a function like this. Now, if we want to find the slope of a tangent line to this function, say a slope at the point 2, 4, okay, the problem here is, to find the slope of a line or of a curve like this, we need at least 2 points to find the slope of the curve, right? But we can basically or simply take a point close to our chosen point on the curve and say m is equal to, say, x squared minus 4 and then x minus 2. So we are taking some point maybe here, and we get a second line. Okay, so let me just wipe this down a bit. Sure. All right. So pick this. Then we have a line going through 2 points. I think this is better. Great. Great. So we have a point here and another point there. So now we have some x squared minus 4, right, over right? All right. So now that we have this slope, so let's simplify this, and then we have x squared minus 2 all squared all over x minus 2. And then we have x minus 2, x plus 2. Okay, so we divide through by x minus 2. Then we have x plus 2. So if we take limit as x approaches 2 of limit as x approaches 2 of x plus 2, and then we have 2 plus 2, and then we have 4. So that is to say that as the values of x approaches 2, we are expecting the limit to be at 4. Okay. Yet we know that if we insert 2 into the original function, the function is going to be indeterminate, right? So that means that for the limit of a function to exist, it doesn't necessarily mean that the limit should exist or should be defined at the limit point. Okay, all right. So let's consider a set of points. So let's consider, say, a point x and then their gradient on the curve. Okay, so we are going to consider a set of points 0, 1.5, 1.9, 1.99, 1.999. So if we insert these values into our gradient formula, we are going to have 2, 3.5, 3.9, 3.99, 3.999. You can take your time and do these computations and then confirm our values. So obviously, you can see that as we insert these values into our gradient formula, we are going to get values that approach 4. Okay, we are going to get values that approach 4. So now that we have our gradient, we've confirmed that our gradient is actually at 4. Okay, so now that we have our gradient at 4, we can boldly now find the equation of the tangent line, right? So we use the point slope form of a equation of a line. So we have, say, y minus y1 plus m to bracket x minus x1. Right, so we can use the points 4, 2, and then say that y minus 2, minus 4 equals 4, oh, no, this is 2. For x minus 2. So in that case, we have x minus 2 equals 4x minus 8, right? And then y equals 4x plus 6. So this would be the equation of our tangent line. Okay, so somebody may be asking, what was the second line I drew earlier? So the second line basically is a line that cuts a curve at 2 points. Okay, so you can see that the closer we draw so the point was here, so point was it 4.24? So the 0.24 was here. Point 24 was here, right? And then we pick a point here. So we realize that the closer this point, or let's name them P and Q, the closer P gets to Q, then we are actually approximating the slope of the tangent line. Okay, so the more Q approaches P, we are actually approximating the slope of the tangent line. So let's consider this very simple example. So suppose that a ball is dropped from the upper observation floor of a tower which is 450 meters above the ground. We need to find the velocity of the ball after 4 seconds. Okay, so Galileo, who was a very famous physicist, deduced that the distance covered by the falling object is equal to 4.90 square. Right. Okay. So the problem here is we can find the distance at a point, but there is no change in distance, right? And we know that to find the velocity of the ball, we need to find the change in distance of the object. But here is the case: we have st, and then after 4 seconds, so after 4 seconds, we have S4 equals 4.9. 4 squared. Fine. So what we can do is we can take a point which is close to the fifth second that the object fell. So let's say we can pick a point 5.1 seconds after the object fell, and say that so we have average velocity being equal to the change in position over the time elapsed. So the change in position, let's just say that, let's just choose a point 0.1 seconds after the 4 seconds. So we can say 4.9 times 4 squared. No, say 4.2 minus 4.9 4 squared. And the difference will be what? Will be 0.2. So then we have 40.18 meters per second. Right. Okay. So now, when we talk about limits, then we have to talk about one-sided and two-sided limits. Okay. So let's look at this Heaviside function. So this is called a Heaviside function. Heaviside functions are mostly used in electrical systems, I have used the Heaviside function to design an electrical switch, okay, which turns on and off when needed. So let's say the function looks like this, right? If t is less than 0, and if t is greater or equal to 0. All right, so a graph of this function will look something like this. Let me say we have this. So now this, then we have this. Great. So now this So this function says that when we approach 0 from the left, that is x approaching 0 from the left, the function approaches 0. Okay, that is L equals to 0. So it means if we have limit as x approaches 0 from the left, g of t is equal to 0. So from the left. So this notation is used when we want to say a function approaches or a variable approaches a value from the left. So now let's look at this function again. So if you have limit as x approaches 0 from the right, g of t will be equal to 1. Okay, so for this is actually a two-sided. Okay, so these are each sides of this function. Okay, now since let's say this is L1 and this is L2, since L1 is not equal to L2, according to the rules of limits, the function or the limit of the function does not exist. The limit of the function does not exist. Right. Great. So this explains the left limit and then the right limit. Now let's look at an example which involves a two-sided limit. Okay, I think I have to quickly clean the word. Okay, so let's look at an example, a two-sided limit. Okay, so let's consider this graph. We have this. Okay, again, note that this is a rough sketch. All right, so now let's look at this graph and say you have to use the graph to find if the values of the limit exist and what the values are. So let me say use the graph to state the values if they exist. Okay, so we have A, we have limit as x approaches 2 from the left, g of x, B, limit as x approaches 2 from the right, and then limit as x approaches 2. Okay, so now let's look at the first part. So when we approach 2 from the left, okay, this here is 2. So we are approaching 2 from the left. So we come all the way here, and we see that when we approach 2 from the left, the value is actually 4. So limit at x approaches 2 from the left, g of x is equal to 4. Yet, limit as x approaches 2 from the right. So if we approach 2 from the right, we have this curve here. So from the right, the function actually approaches 2. So we say g of x is equal to 2. Now, the final part. So does the limit of the function exist? So limit as x approaches 2 g of x. Obviously, since L1, L2, since L1, since L1 is not equal to L2, we say the limit as x approaches 2 of g of x does not exist. Great. So you can try this on your own. Try this. Limit as x approaches 5 from the left, g of x, b, limit as x approaches 5 from the right, g of x, and then c, limit as x approaches 5, g of x. Try this. Now, obviously, we can see that for limit as x approaches negative or 5 from the left, sorry. So where is 5? We have 5 here. From the left, the limit is actually approaching 3. So we have 3 here. Now how about from the right? So from the right, we have the limit approaching 3 again. See? So now that we have L1, we have L1 equals L2 we say that the limit that x approaches 5 exists. Right? Great. So let me clear here and then we can continue. Okay, so now let's talk about the final part, which is infinite limits. Infinite limits. Infinite limits are represented by the form. We have limit or lim as x approaches a, f of x is equal to infinity. So as an example, let's consider the function y equals 1 over x squared. Right? So for this graph, if you consider values from the left of this curve, you realize that from the left, as the values of x increases, the value of y increases and becomes asymptotically close to the vertical y-axis. Right. And the same thing happens when we move. So basically, we'll end our topic for limits here and continue some more solutions in another video. See you later. Bye-bye.